Will be from Dr. Peter Clark. He is the leading researcher at Allen AI Institute in Washington. So please mind that it's 8 a.m. at Dr. Clark's Seattle location right now. And right now it's here 7 p.m. So it's like almost the whole globe away from us. And Dr. Clark will tell us about the Aristo project, about question-answer system. And without further ado, I can gladly pass the word to Dr. Clark.
Great, thank you very much. Good evening to you over in Russia. As Alex says, it's early in the morning here, so I'm very happy to talk to you. Let me share my presentation. And I will share the screen.
Yep, the slides are online.
Good, all right. So my name's Peter Clark. I'm at the Allen Institute for Artificial Intelligence. I'm going to here's an overview of what I'm going to talk about. I'm going to briefly describe the Allen Institute and Project Aristo, which is the project I manage, working on question answering. And then I'm going to talk about three approaches to question answering. The first is information retrieval and statistical techniques. And I'm going to go fairly quickly through some of the techniques we've been using. And then I'm going to talk about our attempts to try and get the computer to reason at a deeper level about questions and answers, one using inference rules and one using a representation based on tables. So this is the outline. So firstly, let me just introduce myself and the Allen Institute to tell you who we are. So AI2, the Allen Institute, so this is a very unusual organization. It was created in 2014 by Paul Allen, the co-founder of Microsoft. It is a not-for-profit research institute, and Paul Allen really wants to see the creation of intelligent machines within his lifetime, and he's created this institute to research some of the very challenging areas of artificial intelligence. And in particular, we're working on systems that have reasoning, learning and reading capabilities. This arrow here points to our building, and let me just switch on a little laser pointer here. So this is the building where we are, and this is in Seattle. So we have this nice view over the lake to downtown Seattle over here. Currently, the Institute has about 50 people. We're still expanding, and we have 4 major research programs. The first one is Aristo, which is the program I manage, dedicated to reasoning about science questions. The second one, just to mention these other ones, is called Semantic Scholar. This is trying to search for technical information in the academic literature, but trying to do better than keyword search, trying to extract knowledge about the contents of the technical articles to give a better search. The third big program is computer vision, trying to extract knowledge from images and videos. And the last one is Project Euclid, aiming at solving math and geometry problems. So although these projects look fairly different, they all concern the intersection of language, knowledge, reasoning, and vision. And so the whole institute is dedicated to working out how these different technologies should work together. So I'm now going to go and talk about Aristo, which is the project I manage. So the goal of the big vision of Project Aristo is that of knowledgeable machines. So at some point in the future, we will have machines that have large amounts of general and scientific knowledge available, stored not just as text, but in a way that can be computed with. So we are not just answering questions by retrieval, but the machine can do some reasoning and explain its answers. So this is what we're striving towards. And then our pragmatic focus, our initial focus is on simple areas of science. And as a initial metric and focus for driving our work forward, we're working on science exams. Currently, we're working on 4th grade science exams, that is exams that a 10-year-old or a 11-year-old person would take. And now we're expanding to the 8th grade science questions. And these are very, very interesting and exciting questions. Many of them are really difficult for machines to answer. If any of you participated in the Kaggle competition that we hosted, you'll know that a lot of these questions require knowledge and reasoning to answer, and that makes them very interesting to us. They appear to be an AI hard challenge. As many of you know, we launched a challenge problem last October, the AI Science Challenge. These were looking at 8th grade questions, that is questions for a 13-year-old or a 14-year-old person. So these are harder questions than the ones we're working on internally. One of the most interesting things about this was the progression with time. If you look at this graph here shows the progression of the scores over time. So initially, the first systems had scores of about 25 or 30%. These questions are 4-way multiple choice. So a random guessing would get you 25%. And as you see, the scores gradually go up over time. And then towards the end of the competition, they were approaching about 60%. So this seems to be a kind of limit that people hit when using statistical and information retrieval machine learning methods. The people who participated, I'll just mention what techniques a few of the winners used. So almost all the winning systems used information retrieval measures. Gradient boost was very helpful. All the winning systems used an ensemble of models to answer questions. The selection of text corpora was very important. People discovered some useful resources, so use of flashcards, a collection of text cards with questions and answers on turned out to be useful. Learning to rank algorithms were very important, and some people used negation or in the questions to help re-rank some of the answers. So these are all techniques which helped in the top systems. Interestingly, use of knowledge resources didn't help a lot, and I know people did a lot of work on deep learning systems, and they didn't make it into the top systems. So here are some conclusions we drew from that competition. So firstly, science questions are a really great challenge for AI. They're motivating. It's fairly clear how a system is doing. It's a task which everybody can try. On the good news, information and retrieval and statistical methods are very powerful. So we can look at the 60% score, and that's a pretty impressive achievement on these questions. On the other hand, there's a flip side to this. We could say, well, even with 750 teams and several months of work, people only got 60%. So clearly there's something more that's needed in order to do well on these types of questions. So let me turn to the bigger question about how can we answer science questions. So if we look at this question as an example, in New York State, the longest period of daylight occurs during which month? June, March, December, or September? So the answer here is June, because the longest period of daylight, at least in New York, occurs during June. So how could a computer answer this question? So one approach is to say, well, maybe somebody wrote down the answer to this question. So maybe we find a sentence saying New York's longest day is June, or maybe we can find that longest daylight co-occurs with June a lot. So this is one way, an easy way of answering the question, but of course it's limited. It assumes that the answers to all the questions we care about have been written down somewhere. A more sophisticated approach might be to do some simple reasoning. For example, if you're in New York, then you're in the Northern Hemisphere, and the longest day in the Northern Hemisphere is in June, so June is the answer. So this would be a more sophisticated reasoning. And then at the other extreme, we could imagine building a sophisticated physics model of the sun and the planets and how the planets move around, and look at the angle of the Earth against the sun to decide how long the daylight would be. And so what we've been trying to do at AI2 is to gradually move up this chain of sophistication, starting with the information retrieval and statistical measures, move into semi-formal reasoning, and ultimately get to advanced modeling techniques. So far, we've done a lot on this information retrieval level, which I'll mention briefly, and then I'm going to spend most of this talk talking about some of these reasoning methods to try and get us beyond the levels which a statistical system can perform. So this is an overview of our system Aristo, and what I wanted to point to was it's an ensemble system. We have, down here we have 5 different solvers that work together, and then a logistic regression module that combines their votes together. And I'm going to talk through each of these 5 systems. These 3 at the top are using information retrieval and statistics, and then these 2 systems at the bottom are trying to do semi-formal reasoning. So let me talk first about the information retrieval and statistical systems. I'm going to start with this first module, which uses a simple information retrieval measure for answering questions. This is a technique that was used a lot in the Kaggle systems as well. It turns out to be surprisingly effective, even though it's very simple. So the basic idea here is simply, given a question and a particular answer option, is that question plus answer option written down somewhere in the corpus? So the algorithm searches a corpus, finds sentences which seem to match a question plus an answer option, and then it'll select the option where there's the best matching sentence. And there's a couple of tricks that are important for this. So the sentence which matches must at least have some intersection with the question, the body of the question, and some intersection with part of the answer in order to ensure that it's relevant. At AI2, we've used a collection of corpora in order to perform this search. We used the Lucene search engine for this. We used a study guide of 4th grade science, a collection of books from the CK12 website. We used Wikipedia, and we use a crawl of the web, which contains 2 billion sentences. So these are the corpora we used. And this is just an example here to just give a flavor of how this works. So in this example here, the question says, the function of a plant's roots are to support the plant and either make food, produce fruit, or taking water and nutrients, which is the right answer. And so the system here has found a sentence in one of our corpora that says the roots of the plant taking water and nutrients. And you can see here, there's a very close match between this sentence here and the question and the correct answer option. We rely on Lucene's matching scores to provide a measure of how close this matches. And that measure of match reflects the confidence that this answer option C is the correct answer. So this shows that if it's a simple question and the answer is written down, we can answer these kind of questions fairly reliably. We've been evaluating our system on a collection of on 6 years of exams for 4th grade science. This is a fairly small question set, but it provides at least a initial picture of how well this is performing. So this particular system gets about 60% on these completely hidden questions. I should add, just to remind people, these are 4th grade science questions rather than 8th grade. When we've tried this on the Kaggle system, our scores go down to about 50%. So this is tuned for these fourth grade science questions. And let me now move and talk about the support vector machine solver and just briefly outline that. So what we did here was we trained an SVM ranker with about 14 features. 6 of these are information retrieval features. So again, we searched several corpora to find 2 things. One is the paragraph of text that best matches a question plus an answer option, and then trying something slightly different, looking for a window of 4 consecutive sentences that best match the question and answer. And then we used 3 different corpora, a study guide, the CK12 books, and Wikipedia, and that produces combined 6 features. And then we also used 8 features from lexical semantics. So what we did was we trained a recurrent neural network language model on a collection of text. And in doing that training, and this text is about 4th grade science, this as a side effect of training the language model, we end up with a collection of word embeddings. That is a vector representation of words, which reflects the word's meaning in the sense, in the context of this language model. And then we essentially use these word vectors to see, is the question similar to one of the answer options? And we do this in 2 ways. One is we add up all the vectors for the question words and add up all the vectors for the answer words, and then compare the 2 vectors and say, are they similar, using a cosine similarity distance. And then another way of doing that is to take all permutations of a question word and an answer word and say, is that question word and answer word similar? Again, using cosine measures, and then we can average that over all the permutations. So again, these are 2 fairly weak and approximate ways of trying to say, of trying to find an answer which seems to have some sort of conceptual similarity to the question which is being asked. And then we repeated these 2 measures for 4 different corpora, a study guide, the CK12 books, the Wikipedia, and a college textbook to end up with these different measures. So how well does this system score? When we add it into our mix here, this scores a little bit worse, about 55%. Again, it's providing a signal as to which is the correct answer, although it's a weak signal. Then finally, let me just, the last of the statistical solvers, I'll just mention the PMI solver. So this uses point-wise mutual information. And the algorithm here is basically to say, does the answer occur unusually frequently with a question in a large body of text? You could think of this as, does the answer fit the question reasonably well? So this is the standard formula of point-wise mutual information. The probability of the question and answer together, if the probability of the question and answer together is a lot higher than the random probability you'd expect if the question and answer had no correlation, then we'd get a high PMI score. So to do this, we take question words, unigrams, question bigrams, question trigrams, skip bigrams, various different fragments of the question, and then look in a large corpus to see whether they occur unusually frequently with fragments of the answer. We use the Waterloo corpus, which is a crawl of the web. It's about 280 gigabytes of text, and the WUMPUS search engine for this. And so this is just to show the kind of scores which come out for an example question. So here's a question. What is the main function of scales on a fish? And the correct answer is to protect the fish. And here are some of the scores that come out by comparing fragments of the question with fragments of the answer. And you'll see here on the screen, scales occurs unusually frequently with the phrase protecting the fish in the corpus. So this has a high PMI of 5.44. And down here, the skip diagram of scales and fish, scales fish, occurs very frequently with protect the fish in this large corpus. So it has a large PMI score. So we combine all these different measures of PMI together to end up with an overall measure. And this says, well, in a large corpus, protect the fish seems to occur very frequently with different fragments of scales on fish. So this is likely to be the correct answer. And again, if we look at our scores, this again scores similarly. I don't have a slide on this. It tends to answer different classes, different styles of question with this solver. And if we combine all these answers together, then using logistic regression, the whole combination scores about 65%. So illustrating that these solvers do tend to work together. So that kind of summarizes some of these statistical approaches. But for people who worked on the Kaggle challenge and anybody who's looked at science, there are some really challenging questions. So let me just show you an example here. So here's a challenging question. Fourth graders, in other words, high school children, are planning a roller skating race. Which surface would be best for this race? Gravel, sand, blacktop, or grass? So the correct answer here is blacktop. So blacktop is a word that describes asphalt, which is the surface of a road. So it's hard and smooth. This question is interesting because it turns out to be very difficult for our statistical methods. First of all, there are simply no sentences on the web that says that blacktop is good for roller skating. And secondly, word co-occurrence methods tend to struggle with this. So for instance, the word grader and the word gravel are highly correlated in text because grader in English also happens to be a word for a machine that is used to smooth gravel roads, and so this gives a false signal. And similarly, if we're looking at word co-occurrence, we find the word race and the word grass are highly correlated, and the word surface and the word gravel are highly correlated. So these all tend to produce the wrong answer. And really, if we want the computer to do something sensible, we want the computer to have some understanding of what's going on in this question and do some reasoning to answer it. For instance, we would like the computer to realize, well, roller skating requires a smooth surface, and the blacktop has a smooth surface. Therefore, blacktop is good for roller skating. And to give another example of a challenging question, consider this question here. A student puts two identical plants in the same type and amount of soil. She gives them the same amount of water. She puts one of these plants near a sunny window and the other in a dark room. So here's a plant near a sunny window. Here's a plant in a dark room. This experiment tests how the plants respond to light, which is the correct answer, or air, water, and soil. So this is very, very challenging for the computer as well. And the computer really needs to know, for instance, if you're near a sunny window, then you'll receive light. Excuse me, I've gone right to the wrong, excuse me, I pressed the wrong button, so let me just get to where I was. So let me just go to where I was. We need to know, being near a sunny window means you'll receive light. If you're in a dark room, you won't get light. And to test an object's response to something requires comparing that object with the something and the object without the something. So again, this is a very challenging problem that requires knowledge. And so our conjectures that we're pushing hard on at AI2 are as follows. First of all, for many interesting questions, some form of reasoning or inference is necessary. Secondly, so we could say, well, where do we get that knowledge from to do that inference? So our second conjecture is much of that knowledge is written down explicitly. And thirdly, it can be extracted semi-automatically from text with reasonable reliability. So what we're wanting to do to try and get beyond the retrieval methods is to take text such as this. So for instance, animals grow fur to help them stay warm. Is a statement in one of our textbooks, and convert it into some kind of inferential or inference supporting form, such as if an animal grows fur, then it will stay warm, where these rules are expressed in some kind of structured representation. So what I'm going to do now is talk about our attempts to do this and where they work and where they break down. So this is part two, automatic extraction and use of inference rules like this. So our conjectures, as I said, we want to do this kind of transduction. And This is a very difficult task. So extracting these kind of rules is very different from trying to extract basic facts about the world. For instance, that Moscow is in Russia or that Paris is the capital of France. These rules are more structured and they involve words and phrases that have rather fuzzy meaning compared with the named entities that you see in databases. And so the approach we've been following is as follows. First of all, do some analysis to work out, well, what exactly are the types of knowledge we need to extract. Secondly, define simple vocabularies or some simple representations for them. Use extractors, run over text, and then use a simple inferencing system to apply them to answer questions. And so I'm going to talk about these different stages. So first of all, in terms of analyzing questions to work out, well, what knowledge do we need in the first place to answer these questions? Consider a question like this one. A fox grows thicker fur as the season changes. This adaptation helps the fox to find food, keep warmer, grow stronger, or escape from predators. Keep warmer being the right answer. So you can look at this question and say, well, it's a question about foxes and fur, but actually there's a deeper piece of knowledge that's needed here. There's an underlying abstraction. This question is really about the purpose of something. So here the question is, well, what is the purpose of fur for a fox? And the author of this question is testing whether the student has knowledge about the purpose of various body parts or various artifacts here. And so this turns out to be one of the targets. We can say, well, the computer at least needs to know the purpose of different artifacts and entities in the world. And we can repeat this analysis and identify other recurring classes of knowledge that come up in these questions. And so we started with 9 initial targets, which seem very relevant to these questions. We need to know about causes and effects, about enablement, about the requirements for certain tasks, part of relationships, and then hypernym, an example of relationships. So these are our initial targets. And then to extract them, the general goal is to take text and run it through a set of extractors to produce some semi-structured expressions of this kind of knowledge. So this illustrates some of the extraction capabilities that we've developed at AI2 here. So we'll take in sentences and we end up with these kind of semi-structured representations. So for instance, if an animal takes in food, this causes an animal to get nutrients. Or if an animal inhales oxygen, this causes an animal to get energy. So how does this extraction process work? Well, we have a set of hand-developed extraction patterns, and I'll just briefly summarize the way this works. First of all, we take the text. We use Stanford's core NLP system to create a dependency parse of the text and do co-reference resolution. Then we convert the dependency parse into RDF triples and store them in a triple store. And then we have about 60 manually authored extraction patterns, which are used to extract these different, they're used to identify when these different relationships are expressed in text and extract the arguments of those relationships from that text. Those patterns are expressed as Sparkle queries. And so the output is a collection of these triple-like structures. And then most importantly, within these triple-like structures, words and phrases from the original sentences are included as arguments. And I'll mention that a bit more in a second. And then pronouns are resolved as well in these structures. So, for instance, in these structures here, animals exhale carbon dioxide. Carbon dioxide is a phrase in the original sentence that was talking about animals that's been retained in the structure. So this is the first step of extraction. This provides a summary of some of the knowledge within the textbook, but on its own it's not enough to answer questions. These are just data structures. What we need to know now is, well, what do these data structures actually mean? What are some of the semantics of these things? So this itself is a very challenging problem. Suppose we take a simple expression like fruits contain seeds. What does this actually say about the world? Does it mean that all fruits contain a seed, or that all seeds or many seeds are in a fruit, or all fruits contain all seeds. There are many different ways of interpreting this. So this is the problem of interpreting generic sentences in natural language processing. So what we've done in Aristo is to take a fairly pragmatic starting point, which is, although there are many ways of reading a statement like this, there are some which occur fairly commonly. And so we've taken the most common interpretation and used that as a starting point. And that is, that common starting point is this for all exists statement. Namely, if something is a fruit, then with some confidence it contains a seed. And similarly, if something's a seed, then with some confidence it will be contained in a fruit. So this is expressed in Aristo in a formal representation language like this here. And we can apply this to more complicated expressions as well. So for instance, in this statement, in order for humans to be healthy, they need to get regular rest. This produces a structure from our extraction system saying human gets regular rest, enables humans to be healthy. And then when we convert this into an inference rule, we end up with two statements like this. First of all, for all healthy humans, with some confidence, they will be getting regular rest. And similarly, for all humans getting regular rest, they'll be healthy with some confidence. So this is the basic principle by which we can generate these extraction rules. So a second problem that comes up is about word senses. So what exactly do these word senses mean? So traditionally, in artificial intelligence, people map words and phrases to a hand-built ontology. So we say the word animal maps to the concept of animal in some enumeration of word senses or some ontology. This turns out to be very challenging for open domains like science. So it essentially requires building a big ontology, which requires anticipating all the distinctions that we need for science before we even know what the task is. So what we've done instead is a different approach, namely deferring ontology decisions to runtime. And this is the lesson that was drawn from the IBM's Watson system for question answering. So the basic approach here is to preserve words and phrases within the representation itself. So we don't map everything to a formal ontology. We include linguistic elements within our if-then rules. And then only at runtime do we make these ontology decisions. So at runtime, we would say, maybe there's a question about a person and we have a rule about animals. So at runtime, we'll say, well, does this notion of person mentioned in a question, is it a type of animal in the sense of animal used in this rule? And so the advantage of this is we can make context-sensitive, targeted decisions depending on the specific question. And these decisions are made using a special entailment service that looks in a collection of different ontologies and says, well, what is the statistical evidence that a person in this context is an animal in the context of a rule, and assigns a confidence to this equality decision. And then finally, we want to do some kind of reasoning with these rules that are coming out of our system. Clearly, the traditional deductive reasoning is very brittle. If a rule is missing, then the system will fail to find an answer. So instead, we need a reasoning mechanism that will still make progress even if some of the knowledge is missing or if there are errors in the rule base. So what we've done is to develop a inference system which does that, and I'll show this in just a second. It mixes logical and lexical reasoning to do this. So the basic approach here is follows. Consider this question again: what helps humans maintain good health, getting rest, and so on. We interpret the question. We end up with a structured representation of the question and answer. So a human getting rest is represented like this from the question. Now we might have a rule that says if a human gets rest, then something follows. For instance, the human's healthy. This is the structured representation of that. And you can see here, we've kind of been lucky. The representation of the question and the representation of the rules condition are exactly the same, and so this inference rule would be applied. But suppose this question had been rephrased, so it said resting instead of getting rest. So this small syntactic change causes a change in the representation, in the formal representation of the question, and as a result, this inference rule does not apply in a traditional deductive framework. But if we look at it, we can see, well, intuitively, there's a lot of similarities between the setup of the question and this rules condition. So this this question is talking about humans and resting. Oh gosh, I'm sorry, I've gone. I pressed the wrong button again. I'm just going to go back to where I was. My apologies. So there is weak evidence here that this question setup applies to the rules condition. So this question is talking about an agent and resting and human. The condition of this rule is talking about an agent and human and resting. And that you can see there's close lexical similarity between the two. And as a result, there's weak evidence that this rule should apply based on the lexical overlap. And so we can use that as evidence that with reduced confidence, this rule should apply. And later we may come up with strong evidence that resting implies getting rest. And as a result, this rule would apply with more confidence. So the main point here is that when we have knowledge, we can use the kind of logical reasoning we want. When knowledge is not there, we can approximate what logical reasoning is likely to have done using words and phrases in the question. And this allows inference to proceed when even some of the knowledge is missing. So just to illustrate this with another question, what example describes an organism taking in nutrients? And the answer here is a girl eating an apple. So we take this question. So for this particular answer option, we want to know, is a girl eating an apple an example of an organism taking nutrients? We generate this semi-structured representation of the question. Does girl eating an apple imply an organism is taking in nutrients in this structured form? So we start with a girl eating an apple. From this, we can infer that therefore an animal is eating. Now, one of our rules from our extraction says if an animal eating has the effect of an animal getting nutrients, so we can infer that an animal gets nutrients. And from that, we can infer an organism takes in nutrients, again using this lexical matching service. And as a result, this implies that the other part of the rule actually holds with some degree of confidence. So this is illustrating how essentially a single rule extracted from our knowledge base, coupled with some structured interpretation of the question and answer option, allows us to compute a confidence in this particular answer. So how well does this actually perform? So when we plug it into our system, again, the system is performing approximately similar reasoning, and when we put it in the combination, we end up with a small improvement again in our overall scores. And most importantly, when we look at which classes of questions are these solvers answering, we find there's a substantial difference. So the rule system, which is the one I've just described, if we look, for instance, how the rule system overlaps with, so that if we look at the questions the rule system gets right, compares with the rules that the information retrieval system gets right, only about half the questions are in common. And so this is a good thing. What this is saying is that the rule system is working well on different types of questions to the questions which the information retrieval system is getting right. And that's desirable because that means that there's some non-redundancy in the ensemble, and the systems altogether perform very well. So let me just give some critique about this attempt to use rules. So the good news is it's very cheap to extract a lot of scientific knowledge. The inference supporting aspects of the rules is very desirable. On the other hand, there are several problems. So as you might guess, these rules tend to be very noisy. Some of the rules can be incorrect. So for instance, statements that says animals need air to survive translates literally to a rule that says if animals need air, then the animal survives, which is not really what we want. What we want to say, if animals have air, rather than animals need air, then animals survive. There's no context taken into account, so we end up with weird rules like this one. If the process continues, then the rocks break down. This is kind of clearly nonsensical, but and it will cause damage to the reasoning system. And then probably the most serious problem we've been wrestling with is we have fairly patchy coverage of the domain of science, even with lots of text. And there's no systematic organization. We end up with a giant collection of rules without any structure or organization. So just to illustrate that, here's to show just a random snapshot of some of the rules in the system expressed in English. We end up with rules like this. So some of them are okay. So if an offspring grows up, then the offspring looks like its parents. I mean, that seems reasonable. You end up with strange rules like this. If you teach them, then them learns. I mean, it's sort of reasonable. And then we have rules which just don't make sense. If the lungs have, then the lungs work harder, and so on. So we end up with this rather strange collection. And so this has led us to look at more systematic organization of science knowledge, and that's what I'm going to talk about next. So this is the last thing I want to talk about, which is the use of table-based representations of knowledge. And so this is moving to talk about this last solver within our ensemble. So let me just give another example of a question and try and motivate the use of tables. So this question asks, which unit of measurement can be used to describe the length of a desk? Centimeters, grams, liters, or degrees Celsius? So the answer here is centimeters, but there's this question, if you go to the section in the book that talks about units of measurement, it will talk about different measurements, different units of measurements, different measuring devices, and so on. And we can summarize some of that section of the book as a table, which might look something like this. There are measuring instruments, stopwatches, calendars, they measure different types of thing. There's different quantities that are measured and different typical units of measurement. And so thinking of the required knowledge as a kind of organized collection of tabular information like this, rather than just a large number of rules, provides a bit more of a structure and a handle on what knowledge we need and what is there. And that can allow us to more systematically collect and encode and validate knowledge like this. And to go back to an example I mentioned earlier, a slight variant here, in New York State, the shortest period of daylight occurs during which month? December. Again, we can say, well, we need knowledge about geography and orbital events. So for instance, we need to know maybe about when the different summer solstice and winter solstices occur. We need to know in which hemispheres these orbital events occur, and we need to know some basic geography, and then we need some general rules to connect these tables together. And so this gives us a motivation to say, well, let's try and use a collection of tables to encode some of this science knowledge, and then look at reasoning algorithms that will try and connect these different elements of table knowledge together. So we have a big project underway now to collect a table store, a knowledge base of fourth grade science knowledge encoded in tabular form. So tables are a more systematic organization of knowledge. How are we going to get these tables? Well, clearly it's unscalable to collect them automatically. Doing them fully automatically is a noisy process. And so we're developing an interactive tool to rapidly populate these tables. The idea here is to use relation extraction technology, but in an interactive fashion. So this interactive tool, it operates over a large corpus of about 10 million sentences. And the main observation here is that these extraction patterns that I mentioned earlier, which were executed automatically, you can think of these as runtime queries over a corpus, which can be then refined and validated by a user very quickly. So we're looking at human-in-the-loop elaboration of these extraction patterns to do this. I won't show the full table, I'll just show you a couple of examples. This is just a screenshot. Here the user's defining a table about material and energy conductance. And here, this just shows a query executed, looking for what types of material conduct what types of energy. So the system's searching through the corpus, it's offering suggestions, and the user's flagging positive and negative examples to rapidly train an extraction system. So we've used this to build currently a sort of medium-sized collection of tables. It has about 100 tables in about 10,000 rows, about 30,000 in cells, which gives us a small core of structured knowledge about fourth grade science. The thing which is great about these tables is they are regular, bounded, and we can measure the degree of completeness to which we've captured different aspects of knowledge. So given tables, how do we actually use them for answering questions? And so we've been developing a inference system which uses integer linear programming for this. And so the basic question here is, given a question and an answer option, does a table row or a joining or combination of table rows express the knowledge that's described in the question and answer? For inference, can we join two rows together in a coherent way? And so the idea with integer linear programming is to sketch the kind of alignments that are done, and this picture at the top kind of illustrates that, as a valid and strong support graph. So the support graph says different elements of the question align with different cells in a table, and different elements of one table may align with different elements of another table. So this structure together we call the support graph. And the search problem then is, can we define a set of soft constraints on what makes the support graph good or bad? And then if we can use integer linear programming as an optimization technique to find the best support graph. And then we can score the best support graph and then pick the option which has the best supporting graph. And again, just to give an illustration of how that works, let me return to this example. In New York State, the shortest period of daylight occurs during which month? So the inference procedure is to first of all try and align elements or chunks of the question and answer options with different elements of the table store that we have. So firstly, the answer options here align with a table about seasons and a table about different orbital events, different solstices. And similarly, elements of the question align with different elements of the table. So New York State, for instance, is mentioned in a table about countries, and daylight is mentioned in a table about orbital events. And now we can also say, well, which elements of these tables align with other tables? So we find that New York State, it talks about USA. Similarly, USA is mentioned in a table about hemispheres. And similarly, the table about hemispheres includes information mentioned in this table about orbital events, here talking about northern hemisphere. And similarly, this mention of solstices in this table is also mentioned in this table here about orbital events. So what you can see here is we're creating an alignment of question elements with tables and table elements of one table with table elements of another. And finally, we can look at how answers align here as well and produce this kind of structure. So this structure is what we call the support graph. And it essentially constitutes the proof that the tables connected together express the information that a question plus correct answer option is stating. And so what are the constraints that we use to define a good graph? So these are the basic interlinear programming constraints. So first of all, the basic units of alignment, as I mentioned, they're chunks in the cells and headers of the tables, elements of the question, and elements of the answer option. And here are some examples of the constraints. So the question must align with at least one cell in a table. And then an answer option must align with at least one cell in the table. And then for a table row to be useful in a proof, we must have at least two cells in a row to be aligned, and so on. So we define a number of these constraints. And then there are semantic constraints that only certain elements of the column pairs are semantically meaningful to join. So this describes the integer linear programming model. And this is used to execute queries and answer questions on our data set. So how well does this perform? Again, going back to our experiments, we ran this over on our 6 years of hidden exams. Again, the table system provides a good signal of good answers. And when we include it in our ensembler, we end up with an overall higher score of about 71%. So this is a really exciting result for us. We're getting a sizable boost from methods that are taking us, at least initially, beyond the retrieval and statistical models that were used that I described earlier. So let me just finish off and just tell you just a little bit about our ongoing trajectory and some of the things we're working on currently at AI2 within the context of Aristo. So the first is we're pushing hard on this table store. I described a kind of manual analysis process to describe how these tables are constructed. We're working on new techniques to try and extract some of these tables at runtime based on questions. Secondly, this notion of comprehensiveness of a knowledge base. We're working on formal methods to quantify exactly how comprehensive a knowledge base is. Thirdly, I mentioned a system for rules and a system for tables. Currently, these are totally independent solvers in our system. We're looking at ways of integrating those better together. Thirdly, we're starting to work on direct answer questions. These are questions which are not multiple choice. And then finally, and this is another very exciting area, we're working on answering questions that integrate textual questions and diagrammatic reasoning. So this is integrating some of the work that the vision team is doing with our work on language processing. So I'm just going to close at this point and give you a summary, and then I'll open it up for questions and see which additional questions you have. So I've talked about our goal. We have this big goal of machines with computable knowledge inside. I mentioned elementary science as a great domain which exhibits this challenge, talking about fourth grade science. And then I've talked about Project Aristo, trying to explainably answer questions and different ways of extracting inference supporting knowledge for this. I've talked about two styles of inference supporting knowledge, rules and tables, and described the algorithms we're using to apply these. This is a great domain to work in for people interested in pushing AI forward to make great progress. I do think science questions are a great domain to work on because they really test both the strengths and the limits of existing technologies, and there's a lot of opportunities, I think, for creative, imaginative solutions to solve some of these problems. So I'll stop there. And so I'll switch to the video mode. Thank you very much.
Okay, so questions? I wanted to start myself, but let me first give the question to my colleague Ivan. Можешь подойти потом к видео?
Hey, Peter.
Hi.
It's Ivan. We've met about a month ago at AAAI.
Yes.
Okay. Since your competition on the 8th grader questions is over, could you share with us something that the top competitors have done, which was very different from everybody else? And if you've gained some insights from their solutions that you're going to share, anything?
Yes, I can give some brief summaries. So it was actually striking that most of the winning systems used fairly similar techniques. They all used ensembler methods, using information retrieval methods. Using gradient boost was a very common technique amongst the winners. And using ensembler methods was a good method. I would say some of the things which surprised us, which we weren't expecting, these aren't huge insights, but they're interesting insights. So one insight was the choice of which text corpora to use turned out to be very important. So some of the winners went quite a lot of lengths to customize the corpora they were using, more than we've done at AI2. Secondly, I mentioned the winners they discovered these website of flashcards, so large question and answer sites. Those turned out to be very effective, and that was also interesting to us. One winner used, instead of trying to score all 4 answer options, they reformulated the problem as a 1 versus rest or 2 versus rest collection. So instead of just saying, is A better than B, C, or D, they would say, is A and B better than C and D, or is A and C better than B and D? So they would do some grouping of the questions like that. That proved to give a good signal. And then there weren't many people who got into the syntactic structural analysis of the question. There was one of the winners who, as I mentioned, did some work on negation. So if there were questions like which is not the best answer, or there would be statements in the text which include negation, they did at least some simple syntactic processing of negation. So those were the sort of small insights that came in. In a way, this might have been a question about the way we set up the problem. There weren't any major breakthroughs in AI that came out of this. This might have been partly that the competition was only over 4 months, that there wasn't a lot of notice given before we started. Let me just say, we're planning to run another competition. It's going to be much bigger, and there'll be a much bigger prize. It'll probably run over a year or two, with even more dramatic prizes. So for people who enjoyed the Kaggle competition, we're very excited about it. We're currently thinking very hard about how to scale it up to make it a really big, sustained thing, and one where ultimately we hope to provoke and promote radical new thinking as well as refining existing techniques.
Okay, thank you. And are you going to publish anything based on the competition?
Yes, so there will be a report that's going to come out, I think in the next couple of weeks. We'll give a detailed summary of the systems. So all the winners have sent us a detailed report about what they did and what worked and didn't work. Those are on the Kaggle website, I believe either now or they will be very soon. And the winners have also made all their software public available. So I believe if you go to the Kaggle website, there are links to the GitHub repositories where you can dig into and see exactly what the Kaggle winners did. So this is great for people who are interested in, like yourself, who are interested in seeing more about what they did. This is great that the winners have been so forthcoming and provided all their details very openly.
Okay, thank you very much.
Hello. I would like to ask you a question about these inference-based methods which you mentioned at the end of your presentation. And my question is, what is the advantage of using method you described over the populating these tables with some ontologies which we already have? So it seems like that if you have a number of ontologies, you can populate these tables much more quickly. Is it better quality or worse quality, or why do you choose a little bit different method?
Yeah, that is a great question. The main thing we're wanting to get is a system that scales. So essentially there's a cost-benefit trade-off with building these tables and these rules. To simply build them all by hand would just be prohibitively expensive. If we were working in a very constrained domain, conceivably somebody could build these tables by hand. But when we're wanting to cover a lot of science, there's just too much knowledge that's needed. I should add as well, you'd think fourth grade science is a relatively bounded domain, but in fact many of these questions rely on large amounts of common sense knowledge. So for instance, we need to know that, what a roller skate is, and that it's, and we need to know what a stone is and a rock is and characteristics of water. So there's a large amount of knowledge. Having said that, automated methods, like you say, are noisy and unreliable. So our current bet is to use interactive methods where we do have an ontologist in the loop, but we use kind of fast semi-automated extraction tools that will extract information from text, show it to a person, and then have a person review it. But I would say we're still trying to find the right balance here. We want high quality, but we need scaling. And I think some sort of interactive, semi-automated interactive system is the right way to go.
Okay, thank you. And I have another question. Can you comment what you have used, maybe some of these methods you described here, for your search engine for the scientific papers which were announced recently?
So you asked me to comment on the Semantic Scholar project?
Yes, I think so. Maybe I don't remember exact the name of the.
I see. Yeah. So currently, I mentioned very briefly at the beginning, we have another project here on Semantic Scholar, searching for technical articles. Currently, those two projects are relatively independent. So the search technology that's been using there uses the same kind of Lucene-based search algorithms. The information extraction techniques to try and extract some of the semantics out of papers is fairly tailored towards technical articles. So for those articles, we're extracting things like the class of paper. Is it a survey paper or an experimental paper or a historical paper? What AI technique is the paper about? What sort of data sets that they're using? I would say, so the Semantic Scholar project is not attempting to do any inference about the content of the papers. It's rather extracting high-level comments. Your question's a very good one, though, because our ultimate vision is that these 4 different projects will converge together. And as the Semantic Scholar works on more detailed knowledge about technical papers, some of the techniques from Aristo will become more applicable to that.
Okay, thank you for your answers. And also I would like to thank you for providing for your Kaggle competition, because it became a foundation for our hackathon here in Moscow. And I hope that it will bring some ideas for your research, from solutions from our participants.
Right, and I should thank you guys for participating as well. I mean, your hackathon was extremely exciting to us. We saw it announced and were tracking it very closely. And you guys, it sounded like you had a lot of fun doing it. It was very, very exciting for us to see what happened and hear about it. So thank you.
Here is my more specific question, not on the organization side. Could you share some insights about the knowledge graph which you are building from scenes? There were several recent articles about scene graphs where you are building like a graph of words from ontologies like Dart. And did you compare them with the recent developments in Aristo, or do you think or plan about integrating them into Aristo?
So we've been following a lot of the work on knowledge graphs quite closely. Like Google has their giant knowledge graph and so on. And not just knowledge graphs, there are a number of other resources out there which have a lot of knowledge that's potentially relevant to 4th grade science. Typically, the knowledge graph work that we've knowledge encoded, firstly, at a fairly factual knowledge. So they'll have, basic facts about the conductivity of different materials and, the capitals of different countries and so on. So the amount of science knowledge that we can get out of them is fairly limited. And secondly, the degree of granularity often has not worked for us. So at fourth grade science, a kid will think of metals as conductors and plastics as non-conductors. The typical knowledge graph representations will give you the coefficient of conductivity for 5,000 different metal alloys, and so it's a very different perspective. Having said that, yes, we are actively pulling in what we can from the resources out there, and certainly some of these knowledge graphs do have at least some information that's needed. So some of the basic information like part-whole information, taxonomic information, that is certainly information we are pulling in to use in Aristo.
Okay, cool. I just remember that we tried to recreate one of the LNAI articles about building these scene graphs. Like, for example, you get a question and you surround it with all the words and all the words from these ontologies, and then you add answers and prune all this graph and try to get some cohesive measures. Right. Sorry, so I misheard you. Yes. So these, so that is another technique we've been exploring. I mean, you can view these both the rule-based reasoning and the table-based reasoning as trying to construct some kind of a scene about the things the questions are describing. So. Essentially, if an inference step infers something new about the question, it's essentially adding an extra node into the representation of the that's being built. So I would say the rule-based reasoning, the table-based reasoning, and then the exploration we had with the scene-based reasoning using these large knowledge graphs are all versions of the same thing. That is trying to create a coherent picture of the situation which the question is describing. The specific scene-based system you're referring to, we've included experimentally in Aristo. It hasn't significantly boosted our scores compared with these other course solvers, and so our current hope is that the table inferencing solver and the rule solver will together be doing something similar to expand on that work. Okay, cool. Thank you. Next question.
Hello, Peter. My name is Alexander, and I first of all thank you for your speech. It was really interesting, and it was easy for listener to follow you, your ideas and your examples. Examples were really good. And my question is about the part of an algorithm that merges examples of different methods. I think it's an interesting part because, as I understand, you cannot just summarize and get some average, because different methods have fallbacks in different areas. So there should be some mechanism of estimating the quality of a result that each algorithm produces. And could you provide some maybe basic idea? How do you do it? Thank you.
That's a great question, and it's a very important question to get right. You're exactly right. You can't just add the scores up of the different solvers. So we use a two-stage logistic regression system to combine the systems, and there's two steps to that. The first is to recalibrate the scores of the individual solvers to correlate with probabilities that they get the answer right. So each solver individually is calibrated on a small set of development questions to recalibrate the scores. And then the actual logistic regression system then uses a collection of features of the question and the answer solvers to work out how to appropriately combine the solver scores and the together. So the kind of features that the combiner uses includes how long the question is the question a multi-sentence question or a single sentence, is the answer option a single word or a multi-word answer, what is the difference in scores for each solver, what is the difference in scores between the top score and the second highest score for a different answer option, and so on. So the result of that is that implicitly the logistic regression system comes up with some essentially a model of when to trust each solver. So for instance, short single, if the question is short and single sentence, it knows to trust the information retrieval solver a lot. If it's a multi-sentence question, then the weights work out that that algorithm is not preferred, and it'll instead prefer the rule-based and table solvers. If it's a question with a multi-word answer, the PMI solver gets highest weighted. So we're training the solver, we're training the combiner module to work out what are the characteristics of the question and the solver behavior, so it can focus on the right solvers at the right time.
Thank you. And one more thing, is there any more method to add to this collection of yours? Maybe any thoughts on this?
Yes. We have a number of research projects going on that are exploring other methods here as well. So we have, I'll just mention two of them. So one of them is, these are two methods that are very ambitious, and essentially they're trying to answer some of these questions without, essentially trying to collect the knowledge that's required on the fly at runtime. So not relying on a pre-built rule base or a pre-built table store. So the first one is trying to do the kind of rule-based reasoning by finding a collection of relevant sentences and then chaining those sentences together. So the way I showed how rules chain together, you could imagine finding sentences which express that knowledge and just connecting the sentences together. So the idea here is that essentially we can extract and apply that knowledge at runtime on the fly. So it's very ambitious. We don't know if it'll work or not, but it would be very scalable if it did. The second project is similar. It's essentially trying to identify, trying to build, you could think of it as building a table on the fly. So this works in a three-step process. It takes the question, first of all, it identifies the topic. So it takes the question and says, okay, this seems to be a question about change of phase of different matter, of a solid to a liquid. Then it tries to find the key concepts by looking at all the sentences that mention phase change and says, well, these sentences talk about solids and liquids and gases, so these must be important concepts. And then it'll look for those in the question. And then the third thing it does is to look for key relationships between those concepts. So it'll look in its corpus of sentences and say, well, knowing what is the initial state and the end state seems to be important. And so it'll construct those relationships. So you can think of it as trying to build a table on the fly, extracted from the corpus, that's tailored to a particular question and set of answers. So that's another method we're exploring. Again, it's not in our core, but we expect it to be built into the core if it empirically seems to give some signal. And then I should just say as well, I haven't mentioned about use of deep learning and neural network methods. We're actively trying to work out how to get deep learning involved in different steps of our analysis process. We don't believe you can just plug in a neural net and things are going to work. However, there are clearly some critical components of what we're doing. So, for instance, training a system to align different texts that mean the same thing, where deep learning could work, and we're actively exploring that. Again, that's not built into the core Aristo system, but I would hope it will be in the next 6 to 12 months.
Thank you very much, and good luck in your research.
Still, thank you.
Thank you.
Good morning, Peter. Thank you very much for your wonderful presentation. I have two short questions, actually. The first one is about PowerSet project. It's a semantic question answering system which was acquired by Microsoft some time ago. So do you know about it? Is it still alive, and what are the plans about it? And the next question is about your Semantic Scholar product. Could you please compare its functionality to search and analytical tools which are developed by Web of Science and Elsevier? I mean Scopus, Engineering Village, Scivel, and other well-known products. Thank you.
Sure. On PowerSet, so PowerSet was acquired by Microsoft. In terms of the state of the project, that is the PowerSet work is no longer continuing. It got folded into Bing, and eventually the key people left. So Ron Kaplan went to Nuance Communications and was running a large natural language project there. So I was very sad to see it not succeed. To me, the PowerSet work was very exciting. They were trying to do intelligent search of the web by trying to extract some degree of meaning from the questions and answers. I think it's, in some ways, this is just my own opinion. It tried too soon to become a commercial product and found itself struggling to show advantage over standard retrieval techniques. We've tried to learn from some of those mistakes here by targeting a more bounded problem to start with. So we haven't tried to do general question answering. We said let's work with a restricted subset and try and get a good handle on that. Yeah, there's just a lot of problems with doing that. So it's an exciting project. It's no longer continuing. I do think they had the right idea, though, trying to extract some semantics and meaning out of questions and the text. They just perhaps tried to go too big too fast. In terms of the analytics of Semantic Scholar, we provide, so I don't know about all the tools you mentioned, compared with, I can give some comparisons with Google Scholar. I should note that we currently only do computer science articles, so we started off with that. Still a huge domain, but we're not doing all of science. And let me just also say, the easiest way to see our tools is to try them out. You can go to s2.alanai.org and try out Semantic Scholar for real. The kind of analytics we do beyond Google Scholar, at least, we'll analyze topics of articles, key themes within an article. We'll extract for experimental systems, what were the algorithms used, what were the data sets used. We're trying to do some analysis of the diagrams and the graphs in the articles, ultimately to be able to compare experimental results. But you can go to Semantic Scholar and say, well, give me papers that used the semi-vowel data sets and show me which systems did best. And for people who cited this article, which are the main citations and which are the incidental citations. We're also doing a lot of work on the citation graph. So we'll do analysis of who influenced who. So if you're interested in knowing who you had most influenced on in the community, again, Semantic Scholar will give that kind of analysis. So a lot of interesting analyses. We're doing a lot of studies to work out which ones are most helpful, which of the semantic features are most helpful. If you try it and have suggestions or feedback, please send them to us. We're actively developing the system. We want it to be ultimately a system which really has some understanding of the articles.
Thank you very much. With pleasure. Bye-bye.
Thanks.
And the last question.
Hello, Peter. Thanks for your presentation. I'm Stas, and the question is, do you know about type theory, and what do you think about using it as a method for rule-based inference?
Sorry, just check out typed query systems.
Sorry?
Which system are you talking about?
Okay, I read now a book for math linguistics where type theory is used for extracting semantic from texts.
Right. Sorry, I didn't hear you the first time. So type theory. So we are. So in terms of information extraction, I'm not sure I can answer your query directly. I'm not sure I can answer that directly. We use a type system within our information extraction system. So our ontology includes a large collection of types of entities in fourth grade science. So part of our ontology is mapped to a collection of about 60 different semantic types, and that's used to help guide which rules should apply or which tables are selected. And then in terms of the linguistic analysis, we're using dependency parsing theory as the main linguistic analysis technique.
Thank you.
Okay, so let's now thank Dr. Clark once again for his time and all this really rich Q&A session. So,
great. Well, let me just say thank you very much for your interest. Thank you for the great questions. And I am very, very impressed by everybody's quality of English as well. I'm glad you were able to follow the presentation. And thank you for your time.
Well, thanks for appreciation. And hopefully, maybe we can even see you sometime offline on one of these events. So
sure.
No?
If you have further questions and other things, please don't hesitate to email me.
Okay, certainly. Okay, so once again, thank you, and have a nice day today.
Thank you, I will.
Okay.
It's sunny out here. I will just show you the, I don't know if you can see here, that's our sunny weather outside.
Well, that's a little sad for us because right now it's dark outside and it's a mix between snowing and raining.
Okay, well, get some sleep and relax after your busy 2 days.
Yep, thank you once again and goodbye.
Bye-bye.
Bye-bye.